तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We continue the discussion on visible surface detection algorithms, or VSD as it is called. Of course, there is another name, hidden surface elimination as well. So, we have so far discussed the concepts based on backface culling, where approximately 50% of the faces are removed. That was at the beginning of this section of the discussion on VSD algorithms, and we basically looked at the z component of the normal vector to the surface, and the sign of that basically decides whether it is a back face or a front face. And then among the various VSD algorithms, we first discussed the z buffer or the depth buffer or z buffer algorithm first, and then of course, we also discussed the scan conversion algorithm, and of course, in the last class we have discussed the depth sorting algorithm, or what is known as the painter's algorithm. Okay. If you remember, in the last class we wound up the lecture with an example, which we will revisit shortly, very briefly again today, to ensure continuity, that what are the 4 tests of painter's algorithm, and then we will look at the examples which we have seen, and a few more examples today about special cases where painter algorithms have to be modified or special care has to be taken for certain distribution of surfaces or polygons which have to be rendered. So, we look back into the slide. These are the 4 tests in painter's algorithm when we revisit them. Of course, the first test is of course that the z extent, which I termed as the 0th test, that the z extent do not overlap, and then the first test says that the bounding rectangles in the xy plane of the 2 surfaces do not overlap. So, look at the rectangles and look at the extent along x and y directions. If that fails, you check whether the surface S is completely behind the overlapping surface relative to the weaving position. Okay. So, because we are going to paint S, and we must check whether it is completely behind an overlapping surface in front of it. And then that overlapping surface, if the test 2 fails, then we go to test 3, which says that the overlapping surface is completely in front of S, in front of the S which is going to be rendered relative to the weaving position. Okay. If again the test number 3 fails, we go to test number 4, which says that the projections of the 2 surfaces onto the view plane also do not overlap. This is close to 1. This test number 4 is close to 1 in the sense that the one was comparing the bounding rectangles only, and the test number 4 ensures whether the projections actually overlap on the view plane or not. So, these were the 4 tests in this order we have to keep checking, and if any one of these 4 tests are passed, then we can go ahead and render the surface S with respect to all other surfaces. Okay. So, we go back to the last few points. The test must be performed in order as specified already, and the condition to reorder the surfaces is that if any one of the 4 tests is true, I repeat, if any one of the 4 tests is true, we proceed to the next overlapping surface, that is, if all overlapping surfaces passed at least one of the tests, none of them is behind the surface S, which must be rendered now. No reordering is required, and then S is converted if any one of the tests is true. However, reordering is required if all the 4 tests fail. So, this we must keep in mind, that any failure of the depth extent overlap and then the 4 tests, if any one of them fail, reordering is mandatory. Okay. So, we look at the case studies as examples of painter's algorithm once again. A couple of them we had seen in the last class. We will quickly revisit it again. This was the case when we have an initial order S1 and S2, and you can know that this says that the S1 has more depth than S2 as far as the viewing direction is concerned. Negative Z direction is the viewing direction. So, from top to bottom is what you are looking, and the order hence will be S1 and S2. So, let us pass through the tests. Here let us pass through the tests, where we first see that the Z extent overlap is the 0th one. Then the first test says that the X and Y extents also overlap in S1 S2. Then whether it says that the S2 is it completely in front and behind. So, that also fails, and the polygons also overlap. So, what you have to do is reorder and change the order to S2 S1, because all the tests fail in this case. So, that was the simplest example which we took in the last class, and I hope you have understood it carefully why all the tests fail in this particular case. Especially the test under 2 and 3 are very important to visualize that the surface 1 must be completely in front, the overlapping surface, and the current surface must be completely behind. Both these tests fail as well as in this case. Of course, the visualization of the other overlapping Z and X and Y extent, and even the fourth test of polygons overlapping is very clear from this particular example. Let us go to the second case, case study 2, where we have 3 surfaces in this order, and we have an initial order S1, S2, S3. Why? Because S1 has the maximum depth in terms of the surface limits, then S2 and then S3. So, that is the order. So, let us pass to the first test S1 and S2. There is absolutely no overlap. If in fact, all the test 0 fails, but the test 1 will be passed, because the bounding rectangles of S1 and S2 will not overlap. So, S1 and S2 in that case can be ordered, and the order can be kept and it could be drawn. Okay. In fact, you can draw it in any order, either S1 or S2 or S2 or S1. We will see that helps later on. So, check S1 and S3 to ensure that you can draw S1 first and then S3. All the tests fail. Why all the tests fail? You can see for yourself, the Z extent there is an overlap, there is an overlap in the X extent or the Y extent also could be, and then neither you can see that if you want to draw S1 and then S3, the completely front and behind tests also will be failing. Okay, because if you want to draw S1 and then S3, we typically assume that S1 is completely behind the S3, and then and similarly the S3 should be completely in front of S1, which is also not true. If you extrapolate these lines, you will see that they intersect, and hence the case when you will find that S1 and S3 all tests will be failing, and even the fourth test also will fail. So, need to reorder. So, exchange S1 and S3, and then you will find that this is the new order which you get. In the new order which you will find that S2 and S3 now must be compared to ensure that can we draw S3 first and then can we draw S2. Okay. Check for S2 and S3, which are the polygons here. All the tests will fail again. Why? The Z extents overlap, the X and Y extents overlap, and since you are planning to draw S2 and then S3, we expect that S3 will be completely in front of S2, which is not. And similarly, since you are drawing S2 and S3, it is completely behind, test also fails, all the tests fail once again, and hence the S3 is not completely behind S2, and similarly is not in S2 is not in front of S3, and so both the test 2 and 3 fail. Test number 4 also will fail, because the polygons do overlap. So, you need a further reordering. So, when you further reorder, the correct order which you will get now is S2, S3, S1. Now, you will see that when you draw S2 and then on S3, also one of the test will pass the front and behind, and then you can draw S2 and S3, and S3 and S1 has already been reordered, and so you can draw in this correct ordering. So, this is how an algorithm proceeds, even if you have more than 3 polygons. If you have n number of polygons, n is a very large number. I keep repeating you, difficult to visualize, but please visualize that not only you have 10 or 100 polygons, but maybe a million polygons. Okay? But what will happen is you start with some ordering, okay, of these n polygons based on the maximum Z extent. Okay? And then what you have to do is start with the first polygon, okay, because it is an order based on the maximum Z extent. So, can you draw the first one? So, this has to be compared with the remaining list. This has to be compared with the remaining list, and if you feel that the test for the first polygon with the remaining, which is basically n minus 1 comparison, so the complexity of this algorithm will typically go to order n square complexity, where typically what will happen is n is the number of polygons. So, you can almost visualize that is the level of complexity which we are talking about, and in fact order n square amount of comparisons is what you make with one polygon n minus 1, and similarly for the other n minus 1 polygons also you have to do that. And what you do with the first polygon, the same thing you do with the other polygons is you need to check whether the rest of the n minus 1 polygons can be drawn after you draw the first polygon. Can you draw the first polygon before? In other words, it means that can you draw the first polygon before you draw the rest of the n minus 1, and to do that you have to compare the first polygon with the rest n minus 1 to ensure that you draw it first, and one of the tests at least must be passed when you are comparing the first polygon with any of the remaining rest. If that is not the case, you need to swap. You need to swap and then restart the checking again. That means you are basically looking among the n polygons, which is the first polygon. The worst case complexity actually can go to even higher order n cube. Okay? But what you are basically trying to find out is which of these n polygons can you draw first. There must be one polygons which are all front facing. Of course, forget the back facing polygons, because back face culling has already been used, and that is what a basic assumption we made for all VSD algorithms. And now after back face culling is done, in the case of Painter's algorithm, we are trying to find out which of these polygons can be drawn first in terms of which is having the greatest depth, it is behind everything else. All the polygons can be drawn after that, whether it is 2 or 3 or 4 or higher 10 or 100 or 1000 or a million polygons. Which of these out of those n polygons can you draw first? Okay? And that is what you need to find out. You could be lucky if the initial ordering based on the maximum extent of the depth works out that the first polygon can be drawn first, but it may not be the case in a very complex scenario. So what you need to do is to reorder if necessary. If the tests are failing, all of them one by one, keep on entering, and definitely there will be one particular case, where you will find a polygon which could be drawn first. So once that is ordered, that is flagged out, then you work with the remaining n minus 1. Okay, and keep checking the same thing sort of thing. So the complexity in the worst case basically can go to order n cube, but typically order n square, and average case complexity is what you can estimate for the Painter's algorithm, n being the number of polygons which are to be rendered. Okay, so this is the key idea. I hope I have given a visualization only with 2 or 3. You can visualize if I take higher and higher now value of n as an example. You can actually work out. I will leave it as an example to combine case studies both 1 and 2 and come up with 4 surfaces and check it out. But you can see that the number of checkings have to be manually done to understand the methodology or the way the algorithm works. That is the key important part. Okay. So let us take now, since we are assuming for the time being that with the help of case studies 1 and 2 you are able to understand the algorithm now, and we will say now some special cases where some precautions have to be taken in the case of Painter's algorithm where things could be very difficult. Let us take this example. Okay. We are taking this example where we are in the process of checking the order which could result in an infinite loop. How will the infinite loop come? There are 3 rectangular polygonal strips, rectangular because it is the polygon, all of them have 4 vertices, that is why it is a rectangular strip in 3D, and one is overlapping the other one, okay, in a sort of a cyclic fashion. As you can see that in some part the red is above the greenish patch and the greenish patch is above the whitish one, and similarly the whitish one is also above the reddish patch. Now you start, let us say, with some z ordering, okay, where there are 3 polygons S1, S2 and S3. There are 3 of these. Okay. I did not level them, but you can level them yourself in your notebook. Okay. S1, S2. So based on some maximum Z depth extent, you will find that you will get some order. Assume you get some order S1, S2, S3. It could be red first and then green, then white, or white, green and red. Whatever order you pick up does not matter. You will find that when you are trying to check, especially the test 2 and 3, because 0 and 1 definitely will fail. The test 2 and 3 also will fail, because you will never be able to find for a pair of this thing which one is in completely front or back, and you will be forced to push one back and cyclically you will come back again. Let us say you start with S1, S2, S3. You will find that you will have to reorder S2 and S1. Then you start comparing with S3. After some time you will find that again you have to reorder S1, S2 back, because all tests are only failing. In fact, you will not be able to find a surface in this case. I just talked about this point earlier, because if you have n polygons, after you arrange them in descending or ascending order of depth depending upon the view direction, of course, you need to find out a surface which you can render first or shade first among the list. In this case, n is equal to 3. If you look into the figure again, you try to visualize which of the surfaces can be drawn first. Now, you see here, in this case it is none, because either you try to draw the red strip or the green one or the white one. If you, any one of them if you draw first, what will happen is the other two will completely overlap the other one, which is whichever is drawn next, and that is never the case, because one polygon is overlapping to some extent and it will be overlapped by the other one. As for example, if you draw the red strip first, what will happen is not only the white, the green strip which is also drawn second will also overlap the red one, and so you will not be able to find out one such surface which can be drawn before the other two. And this is a case what we call as the reordering entering into an infinite loop. I leave it an exercise to check that infinite loop yourself by taking in any order and comparing between pair of these rectangular strips and checking all the 4 tests and reordering again, as we have done in the case of the previous case study. Case study 2, where we took, remember, 3 surfaces S1, S2, S3, and we reordered and we got finally a sequence which passes all these tests or at least one of those, and we got the correct ordering. Here what will happen is you keep on reordering, you will never be able to find out the correct order, because the physical significance of this is you can look at the figure once again and see for yourself that you will not be able to draw a single surface and then draw the other two in any order. Other two does not matter, in whatever order you draw. If you take any one of these 3 and draw it first, you will not be able to get this correct impression of the picture which we have shown in terms of partial overlaps. Look into the figure again. You can take the green one or the white one or red one, any one if you draw it as the first polygon to be rendered, the other two will completely overlap that and you will not get the correct impression. So, this is the physical significance of when checking the order results in an infinite loop, you will never be able to come out, I again repeat, with a single polygon in this case which can be rendered first. Let us look at another example. With just 2 polygons, it is also the same case. As you see here, both polygons overlap the other one. The red overlaps the green portion at some point, and the the blue one, and the blue also overlaps the red. What will happen? You start with some order, absolutely no problem, and then you always keep on reordering. Okay? And that will result in a problem that you will never be able to find out a surface out of even these 2 cases which can be drawn, because if you draw the red one and then the blue will completely overlap the red, or the other case, if you draw the blue and then draw the red will completely, the triangular patch will completely overlap the blue colored polygon. So, these are the cases where you cannot draw any surface at the first and then draw the other or the remaining one. So, this process of reordering of Pentas algorithm fails in this case, because you are entering into an infinite loop. You keep on reordering based on certain constraints and you will never be able to stop. What is the solution? Let us look. This case can be avoided by setting a flag, for a surface that has already been reordered or shuffled. Okay? That means you start with this case of 3 or 2 polygons, and suppose you have reordered any pair. Okay? If the process of reordering, when the process of checking other polygons, if it has to be realtered or altered again, you do not do that. If a flag is set, it must be split into 2 parts. So, splitting a polygon is necessary in this case for Pentas algorithm whenever there is a scope for you to enter into an infinite loop. How will you enter an infinite loop? Let us say the case of that the blue triangle and the red triangle and the blue polygonal patch S1, S2. You start with some order. Okay? All the tests fail, you order them, reorder them basically. Okay? So, you can end up with S2, S1. Check for S2, S1 to see if the tests are passing. You will find all the other tests fail, and then you again go back to S1, S2 again, and that process cyclically will continue. That is the case of an infinite loop, and the physical significance also I have discussed, which means that you cannot draw any polygon before you draw the other or the remaining one. So, how to avoid that? Set a flag. What does this mean? When you start with some order before checking the tests S1, S2 let us say, and you have swapped them, okay, reordered them. And when you do that, you set a flag that the S1, S2 pair has been ordered already once, and the process of checking either with only these 2 or the remaining polygons together in case of 3 or more such cases, if it requests for another swap of the S1 S2 which was already swapped again, if you want to redo that operation, that means going back to the original position, no, please stop that, because you will check the flag and find out that these two polygons have been swapped. What is the solution? You have to split one of these S1 and S2 into two parts. S1 S2, that means there are two polygons, let us say S1 here polygon here, another polygon S2 here, and you keep on reordering, because you cannot draw any one of them. What you drew, one of these, you take the plane intersection of one with the other one and split one polygon into two parts, any one of them, not the both may not be necessary. You can do that, but that will increase the computational burden. You take one polygon, remember a plane can intersect another plane similar to a clipping problem, let us say, which you know. So, it is clipping with respect to a surface, and the two intersections of two planar polygons or surfaces will yield the line. So, use that line to split the polygon into two parts. So, from 2 you result in 3 polygons, and you will see, I will leave it as an exercise for you to draw these cases of overlapping triangles or rectangular strips, where if you split any one or maybe two in certain cases, you will be able to reorder the surfaces correctly, and one of the tests will definitely be passed with this. So, I repeat again, for the second case where you have this red triangular patch and the blue polygon, you could split the red one into two parts, the one which is visible to you and the other on the back sides. And so, now you can draw first the smaller part of the triangle, the red one which is behind, then the blue, and then the red one. That will be the order which will be resulting in this. What do you do in this case? Let us say the red one can be stripped into two parts. Okay. So, you draw the smaller strip, and then finally, the white one also could be split into two parts, draw the smaller white strip, then you can draw the full green one, then the white one, and then the second red part. So, you need to, in this case of 3 polygons, the rectangular strips, it is necessary to split 2 of those polygons. In the case of 2 overlapping, you need to split only one of them, and you will get the correct ordering. Remember, you need to set a flag, so that you do not reorder and enter into a scope of an infinite loop. You need to stop that provision, and so what you need is basically a provision, again I repeat, to set the flag, stop the reordering, because if you do not set the flag, enter reordering mode, you are going into an infinite loop, nobody can stop you, your program will never terminate. Okay, so you stop that process entering into an infinite loop by setting a flag and say, please, I am not allowing it to reorder once again, and I will go for splitting. So, take those 2 polygons and split any one of them. That is a provision which you know by mathematically how to clip one polygon, one plane with respect to the other one. Okay. So, once we know that, that is the particular case of splitting polygons in the case of Painter's algorithm. Okay. What happens in this case? This is also a very nice example. You see here that there are 2 rectangular planar patches, strips again, and S1 and S2. S1 is in blue color and S2 is in blue color, S1 is in red color. What are these values given? You are looking through the viewing plane XY, looking along negative Z direction, let us say, and the values which are given at the vertices of these rectangular strips or polygons, in fact, henceforth I will talk them as rectangular strips in this case, are the Z values of the vertices. XY does not matter, whatever they may be, those are the Z values. So, if you look at the vertices of S2, in fact, the surface S2 is parallel to the XY plane, because the vertices are at 0, it is Z equal to 0. So, it is a planar patch which is parallel to the XY plane. It is not the case for surface S1. Why? The vertices, the bottom 2 vertices have depth plus 0.5 each, and the top 2 vertices have depth minus 0.5 each. So, you have to visualize this scenario, that although surface S1 and surface S2 appear to be like this in this form, one is of course a red color, I will put 2 colors. Okay. Let us say like this, where you have 2 different colors for surface S1, S2, although they are visually appearing, but one of them is just tilted in this form. Okay. Surface S1, let us say, is this polygon which is parallel to your XY plane, your viewing plane, the screen which you are viewing this lecture right now, let us say is the XY plane, and this is parallel to that XY plane, this is surface S1. S2 is not parallel, it is inclined. Okay, it is inclined in a manner like that, that is what you have for S2. So, if you probably view, it will be like this, not like this. These 2 planes S1, S2, if you see, are not parallel to each other, one of them is inclined. Okay, if this is the Z direction, okay, XY plane is like this, one of them is the XY plane, S1, the other S2 is like this. So, this is what you have to visualize. Look again and try to visualize these two surfaces S1, S2. Are you able to visualize now? Difficult, but try to visualize. Again I repeat, S2 is parallel to xy plane and S1 is not parallel to xy plane. Look at the value of the z coordinates of the vertices given for surface S1, S2 next to the vertex. I repeat, 0, 0, 0 is the z coordinate or depth of the vertices of the polygon S2, whereas for the rectangular strip S1 the values are 0.5 for the bottom row 2 vertices, the upper pair of vertices have a negative value of minus 0.5. So, S1 is inclined. Let us go through all the tests here for this particular case. What about the 0th test? Z extents overlap? Yes, they do. Okay, because as you see here, this is S1, S2 here. So, if you look, this is the Z direction. So, Z extent overlap, 0th test fails. So, go to the test number 1. Test number 1 says bounding rectangles, do they overlap? No. If you take the bounding rectangles in this case, S1, S2, each of the rectangles itself is a bounding rectangle. Okay. So, we will assume that although there could be a common boundary between the two, but that we can neglect that to be an overlap. So, test number 1 itself is passed and we can render S1, S2 in any order. In fact, the ordering now will be S1 and then S2. Why? Because that is the extent of the Z which was used to put S1 and S2. Look back again, S1 and then S2, because S1 the prior ordering before the test will be S1, S2. So, you can render it in order, no need to reorder them. Now, look what I do with one of these polygons in the second figure, figure B. This was figure A. Look at figure B carefully and see the variation with respect to figure A. Look what we have done. Okay. We have kept the polygon Z extents same in terms of the Z coordinates of the vertices, that is kept same for both surfaces S1 and S2. Okay. In this case, of course, the same rectangular strips are used, S1 and S2. Z extents are remain same. I rotate surface S2 in the xy plane about an angle theta. Okay, you have to visualize this. Okay, how do you do? Let us look at this. This was surface S1 and you had a surface S2, okay, which is inclined. Surface S2 is inclined, and this was surface S1. This is surface S2 which is inclined. What I am doing basically is taking surface S1 and rotating in the xy plane. I can do that because there will not be any problem of two surfaces intersecting each other in this case, it will not happen. I repeat, S1 is parallel to xy plane and you can rotate that in the xy plane, and you are doing that with the surface S2 inclined in the z direction, all right, but it is adjacent only to your surface, let us say your surface S1, this is S2. So, S1 is now rotated, you can do that. Okay, this is my palm, let us say S1, and it is rotated with respect to S2. Look at the figure once again and see how you can visualize this. From figure A to figure B, you can go by simply rotating the surface S2 in the xy plane, and it will still not intersect. Well, there will be overlap in the xy extent, all right, but it will not cut or intercept or get into the surface S1. The surface S1 and S2 are not intersecting each other still. It is like around the vertex of the meeting point between the two common lines S1, S2, I have given it a small rotational twist, that is S2, and the top part of S2 is now overlapping S1 and the bottom part has been separated out. I hope you are able to visualize this figure B, and the Z extents of the rectangular strips, there is absolutely no change, because for S1 it is the same. I have kept it undisturbed or unaltered. It is only for surface S2 I have given a rotation about the xy plane, and we know when we rotate about the xy plane, the Z coordinates of in 3D do not change. Okay, so that is what happening with the surface S1, that the Z coordinates are remaining same. You have just given it a twist. The other surface S2 is unaltered. Okay, look back now. Let us see the test what happens. As you can see for figure B, that the 0th test failed, because like in figure A, the Z extents were overlapping. So, test number 0 fails. What about test number 1? Now, the polygonal boundaries, the minimum enclosed rectangle for surface S2 will get inside the enclosed rectangle or the rectangle itself for S1. Remember, the minimum enclosed rectangle for surface S2 will not be S2 anymore. It will be a larger rectangle which will get inside S1, or S1 will get inside the minimum enclosed rectangle for surface S2. So, what happens is test number 1 also fails. What about test 2 and 3? Well, if you want to order S1 and then S2, you have to check whether S1 is completely behind S2 and S2 is completely in front of S1. Neither of these cases is happening. You have to visualize in 3D now. If this is S1, this is your S2, and even if I have rotated it a little bit for figure B, you can see for yourself, if this is the Z direction, as you can see for yourself, what will happen basically is that the front and behind tests also fails. Okay? None of them is completely behind the other one is not in completely in front of the figure S2. Okay? So, S1, S2 test number 2 and 3 also fails. The only remaining test now is test number 4. What does test number 4 says? Project these two polygons on the xy plane. As you go back to the figure now, the polygons themselves overlap. The polygon themselves overlap. So, figure 4, I am sorry, test number for figure B, the test number 4 fails as like test number 1 also. Not only the bounding rectangles overlap, but the polygon themselves overlap. So, all the 4 tests have failed for figure B. And so, what do you do? What do you do for figure B? For figure B, there is no other option. As we have did in the previous cases, you have to split one of the polygons. You have to split one of the polygons in 2 parts, use S1 to split S2 into 2 parts, or you can use S2 to even split S1 into 2 parts. I did say when there are 2 polygons, the reordering will take place returning into an infinite loop. We set a flag and say we reorder only once, but not 2 times, avoid that. And in this case, if a second one is demanded, when all the recheck of all the test for 4 tests fail, then you need to split the polygon into 2 parts, and that is what you do for figure B. Okay. So, what you do here, I repeat, use S2 to split S1 into 2 parts, or you can take S1 and split it into 2 parts. You will result in, you will be having 3 polygons now, and you will be able to come with a correct ordering. I leave this exercise for you to draw. Take S1 and split into 2 parts, or even S2 and check the reordering and the testing once again. If you split the rectangle which is surface S1 in 2 parts, you can draw the back side of S1 first, and then the blue one, and then the remaining part of S1. That will be the order which you will get in this particular case. I repeat again, if you split S1 into 2 parts, the back side of S1 first, then the S2 inclined blue surface, and then the front remaining part of S1 is what you can draw, and that will be the correct ordering and the correct impression of this figure which you will get. So, you can only implement that by obtaining by splitting. So, that comes to the end of the painter's algorithm, which was the about the third VSD algorithms which we have discussed so far. We move on to a next concept called area subdivision method. Area subdivision method is the 4th category of the VSD algorithms which we are going to discuss, and the concept says that examine the polygon and divide if necessary. So, this goes straight away into the concept of division, okay, which was a special case of painter's algorithm. In the case of area subdivision, we examine and divide if necessary. And the other key points in area subdivision method are, it works in an image space. What do you mean by image space here? You remember, in both in Z buffer algorithm or depth sorting painter's algorithm, or even scanline, of course, the scanline is a mixture of both, but basically depth sorting painters as well as the Z buffer, we are working in the object space polygon by polygon, and we are only involved in the depth value, surface normal, etc. That will also come, but here we are working mainly in the image space. We will do manipulations of projections of 3D polygons onto 2D, and then work in the image space. Of course, we have to use the Z values, because that is the essence of VSD algorithm in terms of Z ordering. We can't avoid that, but the methodology of working in the area subdivision method works in the image space rather than what we call as object space in the other algorithms. Okay. You remember at one of the beginning lectures of VSD, I did say that I can have 2 broad categories of VSD algorithms. One is object space and image space. So far, most of the discussion was on object space. This is the first time, except the scanline algorithm is probably closer to the image space, although use a combination of both, but it is probably can be visualized as an image space. Area subdivision in fact is a good example of an image space based method by which we render polygons and implement VSD algorithms. Okay. So, come back, we are working in image space, as since we are working with image space with polygons, area coherence is exploited and we divide and conquer, because we did say at the earlier that we have to examine and divide if necessary. So, it is basically a divide and conquer strategy, area subdivision method. Okay. And the algorithm which we are going to discuss, of course, there are quite a few. We will discuss the simplest one, which is known as the Warnock's algorithm for area subdivision method, and we will see how it works. We talk in the case of area subdivision method, a possible relationship of the area of interest, a rectangular area of interest AOI, this means the area of interest is nothing but the area of interest AOI, which is a typical terminology used in computer graphics and by imaging community. Please remember this area of interest. So, we are talking of possible relationships of the area of interest, which is a rectangular area of interest, and the projection of the polygon. So, we are here to compare rectangular area of interest. What is this area of interest? We will see, but for the time being you can visualize that it could be the area entire image, because the image itself is a rectangular area and the entire area of interest could be the image itself, or image itself could be the entire area of interest. So, that is what we are comparing with a polygon, or you can take a small part of an image. If this is the entire image which you are seeing now on the screen, take a small part of the image which is considered as a sub image by imaging technology. People take that small rectangular strip and you are comparing that with, say, a rectangle which you see in the behind, okay, or any other polygon which you draw, you are comparing a polygon with a small rectangular strip. So, you have to visualize. We will see how illustrative examples next as we move on with this course, but for the time being assume that you have a small rectangular strip which could be the entire image also, or any small part of the rectangular strip, and you have an arbitrary polygon somewhere with n vertices, and you are comparing these two in the image space itself to start with. So, that is what we are talking about, possible relationships of the rectangular AOI or rectangular area of interest and the projection of the polygon in 2D. So, it is everything is going on 2D right now. What is done in 2D? Surrounding polygons are completely overlapping the area of interest. That could be one case. Okay. So, we will see what do you mean by this. We will go through these possible relationships in terms of statements and then go to the example in the next slide. We will see these relationships. One relationship is surrounding. Just remember this word surrounding. We are talking of a surrounding polygons which are completely overlapping the area of interest. Remember, this area of interest or AOI is a rectangular sub image or a part of the image under consideration. It could be the full image also to start with. You can have intersecting polygons which intersect the area. That could be another case. We can also have a contained relationship where we say the contained polygons are completely inside the area, okay, and the fourth part is disjoint polygons, where the disjoint polygons is a case where the area is completely outside the area of interest. The polygonal area is completely outside the area of interest. So, these are the four different relationships which we have, between what? A rectangular area of the image, any arbitrary, it is not completely arbitrary, we will see that how to choose that rectangular area of interest, which will be the key part of this area subdivision or Warnock's algorithm. A small rectangular strip is what you choose, and you have an arbitrary polygon somewhere, and you are talking of a polygon, let us say here, and a small rectangular strip. Okay. So, there could be various relationships, and we have seen that there are only 4 of these which cover all possible relationships, and remember these 4 terms which describe the relationships between a rectangular area and the polygon. The first is surrounding, intersecting, contained and disjoint. I repeat, surrounding, intersecting, contained and disjoint. Remember these 4 terms. Now, please note it down. These are the 4 relationships which can exist between these 2 sub areas within the image plane. One is the projection of a polygon in the image and a small rectangular area of interest or sub image or a part of the image. Okay. So, we look into examples which illustrate these relationships. Now, I repeat, look at this slide, we look at examples of surrounding, intersecting, contained and disjoint. Okay. Let us look at the first example. So, we look into the 4 cases of polygon position with respect to the rectangular area of interest. The rectangular area of interest is given by this gray color rectangle, which is could be a part of an image or the full image, and this is an arbitrary quadrilateral which I have drawn, which is the projection of the polygon. And as you can see, that the polygon is completely surrounding the rectangular area of interest, which is this gray color strip, which is not the polygon projection. Remember, you must visualize that this rectangular strip is the area of interest, it is part of the image which we are analyzing or considering, and we are comparing this rectangular portion of the image with an arbitrary polygon, and this shows an example where this polygon completely surrounds the rectangular area of interest, and that is the case of what we call as the surrounding relationship. This is the case of surrounding relationship. I hope you are able to visualize this example. Well, of course, when we probably see other examples, this will be more clear. This is a case of intersecting. As you can see, the projection of the polygon, in this case which is a triangle, now from a quadrilateral I have gone to a triangular polygon, and so a projection of a triangle will be a triangle in 2D, and as you can see, partly this position of this triangular polygon will be overlapping with this rectangular area of interest, which is this gray color rectangle. So, this is an example which illustrates the case of intersecting a triangle with this rectangular area of interest. Okay. So, that is the case of intersecting. Surrounding intersecting, two modes are left, contained and disjoint. This is contained. The same triangle now or the polygon is completely within or inside the rectangular area of interest. So, that is an example which illustrates the concept of contained relationship. And the last one is disjoint, where there is no overlap area between the triangle and the rectangular area of interest. Okay. So, I hope these 4 figures are able to illustrate the 4 possible or 4 different cases of relationships of the areas in 2D between a projection of a polygon and a rectangular area of interest. I repeat, please remember this term: surrounding, intersecting, contained and disjoint. I repeat, surrounding, intersecting, contained and disjoint. If you remember these 4 relationships and think of these illustrations which we have just seen in the previous slide, that is enough for you to go into the steps of the algorithm and visualize what is going to happen. Please look into the slide once again. These are the 4 cases of relationship: surrounding on the left, intersecting on the top right, contained in the left bottom and disjoint on the lower right. Okay. So, I hope you have understood this and also copied it in your notes. Now, we will look into the case of how do you treat these 4 different cases. Treat the interior part of the intersection and contained as equivalent. That means, henceforth intersection case and contained will be treated as similar or same in terms of interpretation of rendering in terms of VSD. What we will do, I repeat again, intersection and contained, how they are equivalent, why they are equivalent. In terms of the algorithm it will be clear, but for the time being let us visualize not in terms of the relationship that they are similar. No, contained is fully inside, intersecting is partly overlapping, mind you. Okay. But in terms of interpretation of the algorithmic steps, we will say whenever we have a relationship which is either contained or a relationship which is intersecting, okay, intersecting and contained, remember that they will be treated as similar. So, that is the first step. We do not worry about the disjoint case at all, it is irrelevant. Okay. We will, whenever we find a disjoint case, we will not worry about that polygon at all. And the decisions about division of an area, remember we are talking of an algorithm which is based on area subdivision. So, you have to divide an area is the question. When do you divide an area? That is the criteria which we will talk about. Look back, the decisions about division of an area is based on the following constraints. If all polygons are disjoint from the area, display the background color, do not subdivide. That is what we meant by some time back saying that the disjoint is irrelevant. That means, just neglect that polygon if it is disjoint and display with the background color. If you visualize a background color like a gray color or a green color which we are seeing on the screen, that is, or it could be a dark black color or a foreground, or the background also could be white. Use that background color if the polygon and that area of interest are disjoint. Okay. That means completely there is absolutely no overlap. So, that disjoint case is irrelevant and all polygons are disjoint from the area, display the background color. Number 2 point says that if there is only one intersecting part or interior which is contained, Remember the first line and the first para says interior part of the intersection and contained are equivalent, that is what you treat them. This is the second point which is related to that first statement. If you have only one intersection part or interior are contained, so these two relationships are same, intersecting and contained. If that is the case, fill the area first with background color and then scan convert the polygon. If you have drawn those pictures which you have seen in the previous slide, which talked about these four illustrative examples of illustrations of the relationships between a rectangular area and a polygon, if you know that already, okay, if you know that already, you know that in the case of a polygon contained within a rectangular strip or intersecting one, if I draw the background color first of the rectangular AOI or the area of interest and then draw the polygon, shade the polygon, then what, of course, within that particular area only, do not draw the complete polygon. Okay. So, you have to clip and find the common intersection part if it is intersecting and scan convert only that part. If you do that, you will get the correct impression of what we have seen in the previous figure. So, I repeat again, first point is very simple, throw away disjoint part, display background color only, and when you have intersecting and contained, fill the area with background color and then scan convert the polygon. So, 1 and 2 steps have taken care of the 3 relationships. The only one relationship which is remaining now to consider, we have talked of disjoint, contain, intersecting, all the 3, which is remaining, overlapping, correct. Overlapping relationship is the one which is remaining between the 2. What do you do when you have an overlapping case? If you have a single surrounding polygon and no intersecting or contained polygon in it, use the color of the surrounding polygon to shade the area. That is very simple. Okay. So, the subdivision has not yet come, we are looking into scenarios which we can handle without subdivision of an area. These are simple cases. Okay. So, we have talked of disjoint earlier, contained intersection under one category. Surrounding, if we have just a single polygon completely overlapping or surrounding the rectangular area of interest, there is no polygon in front of it or on back side, whatever the relationship of other polygons, if those are not there at all, there is just a single polygon which is surrounding that, then you can take the area of interest and display the color of the polygon. Use the color of the polygon to shade that corresponding rectangle only. Okay. So, these are the cases which you can keep in mind in terms of the decision to be taken based on the relationship between rectangular area of interest and polygon. Still, there are other so many cases which are possible, which will cause subdivision. So, any one of these cases occur in single polygonal cases, you go ahead without subdivision, but if there are 2, you have to examine further and subdivide if necessary, and that is what we will see. If there are more than, this is the fourth, the most important point, if there are more than one polygon which could be intersecting, contained in and surrounding, we are not worried about disjoint. I repeat again, disjoint of course, they are irrelevant, we said that earlier, we are talking of 2 or more polygons. If there are more than one polygon which are intersecting the area, contained within the area or surrounding this area. Now, you can have 2 of those, one intersecting, one contained, one intersecting, one surrounding, and all that various relationships are possible, 2 or more, and there are combinations of intersecting, contained and surrounding, okay, except disjoint. Okay. We do not worry about disjoint henceforth. So, more than one polygon could be intersecting, contained or surrounding the area. If this is the case, but we have just one surrounding polygon which is in the front of all other polygons, then in that case also we can fill the area with the color of the surrounding polygon. This is interesting. We have many of those, but still there is one in the front. In fact, one in the front of you which is surrounding the entire rectangular area. There could be others behind which could be intersecting, contained in, but there is one surrounding, one in the front. Of course, if there are more than one surrounding, you have to find out which was in the front. That you have to move to the object space to do that. That is color. But there is one in completely in the front which is surrounding the entire rectangular area of interest, and it is obscuring or occluding all the polygons behind. When you are looking towards me, let us say there is a polygon surrounding in the front and there are smaller polygons contained in and intersecting your back side, then that front polygon could be also used to display the rectangular area of interest. So, one of these 4 conditions are not true, then you need to subdivide the area into more than one part. Okay. Step 4 is implemented, we will see that how it is implemented by comparing the z coordinates of the planes of the polygons involved at the 4 corners of the area, and if all these 4 steps are not true, then of course we need to subdivide, we know that, we will treat that later on, but let us see what we do. If all these 4 tests fail, divide the rectangular area into 4 equal parts, we know that. Of course, you have to worry about step 4 implementation, but you remember that if all these 4 tests, these tests are not like the Penrose algorithm, but you have to go through these 4 tests in the object, in the image space, to check whether we can render the rectangular area of interest AOI with a background color, and then the polygon or the full polygon depending upon contain, intersection or surrounding, that is what we are looking, and if all these 4 tests fail, we subdivide, that is what, into 4 equal parts. So, this is an interesting part where the sub areas are coming. How do you divide an image into 4 equal parts, and recursively keep on subdividing till you reach what we call as the lowest minimum area or maximum resolution of 1 pixel. So, take an area, take the full image, let us say this full image, okay, need to subdivide into 4 parts, okay, like 4 quadrants of image. Remember when we talked about Bressenham's line ellipse circle algorithm, we talked of 4 quadrants in 2D space, that is what you do in the image, okay, and check individual parts. Okay, and see if one of these 4 tests are true, then it is over, otherwise you have to divide each of those into 4 parts. You keep on doing, we will say examples, till you might reach a case where you keep on subdividing so on, not the entire image, but at least a part of it, and you reach the lowest, what is called the lowest level of decomposition. You can get actually a tree structure. We talked of trees, representation of a tree for an image equivalent to octree representation for solid modeling, you remember that. In case of 3D, we had octrees, and that was derived from the logic of quadtrees in the case of an image, okay, into 4 equal. That is what you do, and you can have further subdivisions and so on. The tree might grow along one particular channel at the maximum level of decomposition of this image, as it is called in imaging technology. You may reach the level of a pixel resolution. 1 pixel resolution is what you have. This is a common concept which is also used, the tree level decomposition, not full tree decomposition, but subtrees in the case of what is called as wavelet decomposition, but this is outside the scope of this particular lecture, but you can visualize, I can divide a image space into 4 quadrants and each of these into further sub quadrants and so on. So, you can have a quadtree representation of an image space, and you keep doing that, and the maximum depth where you can decompose, you are reaching the minimum resolution, maximum resolution of the image, or the minimum quantized step of imaging process, which is 1 pixel of your graphic screen, and that is what you see. Recursively apply this logic till you reach the lowest minimum area or a maximum resolution size of a pixel size, and then use the nearest surface in that case to paint or shade, because you cannot split the pixel into more than, you cannot split a pixel at all. So, in that case you use the nearest surface. So, in that case only you go back to the object space, otherwise you are always working in the image space when you are performing this test, subdividing again, performing this test and subdividing. Everything is done in the image space. Only at rendering time, when you have finally known what to render, you go to the object space, find out the shade of the polygon, and then use it to render it. That is where you go only to the object space in terms of depth ordering, otherwise everything is in image space. Let us take this example of trying to find out what is this decision in step 4. You remember what was the step 4 test? We are trying to find out if there is a big surrounding polygon in front of you and it is obscuring or occluding all other polygons in the back side. Okay, it is in front of you, a large polygon covering the rectangular area of interest, it is in front, and all other smaller polygons are in the back side. In such a case, what you need to do is to ensure that there is no other polygon which will be coming out from the back side within that. Okay, so, that is what. So, let us look at this decision step 4, where you will see that there are 3 such polygons, and we are talking about intersection with contained with respect to rectangular strips of this area of interest. You are looking at the ZX plane. So, you have to visualize these dashed lines are nothing but lines which are parallel to Z axis and passing to the 4 vertices of that rectangular strip, passing to the 4 vertices, and you are taking the projection of ZX plane. That is what you look here. Intersection of the first plane, which is the contained polygon with these 4 lines, is marked by the star. Sorry, this triangle is the contained one, and these 4 are the intersections of that polygon with these 4 lines. Then the circular dots represent the intersection of the intersecting polygon with these 4 lines, and if the surrounding polygon is in front. In this case, you are sure that the surrounding polygon is in front because the z coordinates are the maximum and you paint it. But what about the second case? The other case, if you see here, there is a surrounding polygon, but what could happen is there could be a case where there is a intersecting polygon in the back side which is overlapping and coming from behind. Okay. It could intersect at some point, but there could be something coming from behind which is visible. In this case, the decision step could fail, could fail if you are looking at the z extents. Z extents of the intersecting polygon, although the intersecting polygon is behind, but its z coordinates of intersections with these 4 lines which are parallel to z axis are in front of the surrounding polygon. So, this test may fail. It is not a good test to ensure that the surrounding polygon is in front. You remember, the figure shows it is in front, but there is a plane behind you and you are looking into some z extents of a rectangular strip with this intersecting polygon. Some of the z extents have come forward. The polygon may not have come front, but if you visualize an infinite plane intersecting of the infinite plane with the 4 lines parallel to z axis, those intersecting points could come up and create a problem. In this case, you might have to subdivide the polygon. Okay. Subdivide the area of interest and get 4 parts, otherwise that is what you have. And we will stop with this example and continue the next lecture with more cases of area subdivision method, but this is one drawback which you must keep in mind of the decision based on step 4 based on z coordinates, that is the intersection of the plane of the polygon with a rectangular parallelepiped sitting along the z axis. So, it is something like a viewport in 3D which you are seeing here, and you are trying to find out what is the intersection of this polygon with the 4 extents, the 4 lines parallel to z axis of the rectangular parallelepiped. If the z extents is in front, unfortunately for you, then the surrounding polygon you will not be able to detect it. Okay. But in both these cases, you should be able to paint the polygon with the surrounding one. In the second case, as you look back into the figure, you need to split this into 4 parts in the second case. In the first case, not a problem because the surrounding polygon z extents are definitely in front of the other polygons, and you do not need to split. In the second case, you may need to split, although actually it may not be so. Okay. So, we stop with this example, and next class we continue the discussion on area subdivision with some more examples. Thank you very much.